In this video, we'll be learning about higher order derivatives. A higher order derivative is the process of taking the derivative of a derivative. We know that f prime of x denotes the first derivative of a function, f of x. If there's two prime symbols, this would denote the second derivative of a function. If there are three prime symbols, that would be the third derivative. After that, we generally just use the number, so like f to the 4 of x, that's basically the fourth derivative, and so on. Higher order derivatives are basically very useful when looking at real-world applications, such as looking at position, velocity, and acceleration. So for each of these questions, we're going to be finding a higher order derivative. So for number 1, if f of x equals 4x cubed minus 3x squared plus 7x minus 10, we're going to find the second derivative here. In order to do that, you have to find the first derivative first. So we're going to use power rule here. So this is going to give me 12x squared minus 6x plus 7. Now, if I want to find the second derivative, I'm just going to take the derivative of the first derivative. Okay, that's our higher order derivative. So I'm now going to take the derivative of 12x squared minus 6x plus 7. I'm going to get 24x minus 6, and that is our answer here. Number 2. On this one, we're going to find the fourth derivative. Okay, so our first derivative, just using power rule here, this is going to give me 12x to the 5th minus 5x to the 4th plus 12x cubed plus 3x squared minus 2x. The derivative of 18 is 0. Okay, now our second derivative, 60 x to the 4th. Okay, remember I'm just taking the derivative of the previous derivative, minus 20x to the 3rd, plus 36x squared, plus 6x minus 2. Okay, now the third derivative, 240 x to the 3rd, minus 60 x squared, plus 72x plus 6, and we lose that term on the end because the derivative of negative 2 is 0. All right, for our fourth derivative, what we're looking for here, instead of the primes, putting 4 primes, we're just going to put the number 4. Okay, so now we have the derivative of 240x cubed minus 60x squared plus 72x plus 6. All right, so now let's take our derivative. We get 720x squared minus 120x plus 72. And the derivative of 6 is 0, so we are losing a term again. And here is our answer for 2. Number 3. Find the sixth derivative for g of x equals sine of 2x. Notice here that there's a function in a function. This requires us to use chain rule here. So if I find the first derivative, I'm going to get cosine of 2x times 2, or 2 cosine 2x. For the second derivative, I'm going to copy the 2 down. I'm basically looking at this here and taking the derivative of it. Copy the 2 down. The derivative of cosine is negative sine 2x times the derivative of the inside, so times 2. So I get negative 4 sine 2x. Now I'm going to take the derivative of that, and I will show a little bit of a shortcut in a bit. Negative 4 times cosine of 2x times 2, and that's going to give us negative 8 cosine of 2x. Now for our fourth derivative, I'm going to copy the negative 8 down. The derivative of cosine is negative sine 2x times the derivative of the inside, so times 2. And that's going to give me positive 16 sine of 2x. Now our fifth derivative. Okay, so again, just a reminder, I'm taking a derivative of whatever I end up with at the end, my simplified version. So 16, derivative of sine is cosine, keep the 2x, times the derivative of the inside, so 32 cosine 2x. And finally, we're looking for our sixth derivative, so I'm going to take the derivative of that. So that's 32 times negative sine 2x. Derivative of the inside is 2, and I get negative 64 sine 2x, and that is our answer here. We're asked for the sixth derivative, so this is where I'm going to stop. All right, let's talk about how maybe we could have gotten to this answer a little bit faster. If we think about the derivatives, the derivative of sine is cosine, the derivative of cosine is negative sine, the derivative of negative sine is negative cosine, and then we loop back up. So if this is our original, this is our first derivative, second derivative, third derivative, fourth derivative, fifth derivative, sixth derivative. This tells me my sixth derivative is going to have a negative sign, and you could see that in our answer. There's a negative and there's a sign. The 2x in the parentheses is always going to stay the same. So now let's talk about that 64. What do we notice when looking at the problem? Well, look at the first derivative. It was 2 to the first in front, then 2 squared, then 2 cubed, 2 to the fourth, 2 to the fifth, 2 to the sixth. So I could say here, I could take a good guess that using these patterns and these things I noticed, if I was asked to find the eighth derivative, I would have 2 to the eighth. And then let's look at my chart up above here. So my seventh derivative would be here. Eighth derivative would be here. So I'd have sine of 2x. And if I wanted to simplify that, 2 to the eighth power is going to give me 256 sine of 2x. Okay, so sometimes you can notice those little shortcuts instead of writing out all of the derivatives. All right, the last two problems we're going to look at are ones that involve taking a second derivative, but when you have an implicit function. That's where the y is not isolated, or we're not going to easily isolate the y. This is our notation for the second derivative implicitly. And we're going to start by doing the first derivative just like we've done before. So the derivative of 5x squared plus 2y squared equals 10. That's going to give me 10x plus 4y dy dx. Remember, anytime you're doing an implicit derivative and you're taking the derivative of a y term, you're going to get dy dx attached to that derivative with y equals 0. All right, let's isolate the dy dx. So I have 4y dy dx equals negative 10x over, I'll do this actually in separate steps here, negative 10x, and now I'll divide the 4y. All right, now what we're going to do is that's our first derivative. Okay, so notice that is our first derivative. I want to take the derivative of that. The derivative of dy dx is d squared y over dx squared. It's our notation for second derivative. And now, since I have a quotient, I have to use the quotient rule in order to find the derivative. All right, so I'm going to plug all of my original functions into their appropriate places. And now let's fill in the derivatives. The derivative of negative 10x is negative 10. The derivative of 4y is 4 dy dx. Let's clean this up a little bit. So I have negative 40y plus 40x dy dx. You can simplify the the denominator if you want to, so 16y squared. But when we're doing an implicit derivative and we're doing the implicit second derivative, we want it to always be in terms of x and y. We don't want a dy dx in here. So I need to get rid of this dy dx, and look up here, we already know what dy dx is. So I have negative 40y plus 40x times, let's substitute, negative 10x over 4y all over 16y squared. And there is our second derivative implicitly. You could choose to simplify it and get rid of the complex fraction, but for the sake of just focusing on the higher order derivatives and not the algebra, I'm going to leave it like that. All right, last problem. Similar idea, look for our second derivative. The difference here is I have product rule. I can see that I have two functions being multiplied. So using my product rule, the derivative of the first term is 3 times the second, plus the first term times the derivative of the second, that's dy dx, plus 2y dy dx equals 0. All right, let's get all of the dy dx's alone on the left side. So I'm going to move that 3y over then. And since I have two dy dx terms, I'm going to factor out dy dx on the left side of the equation. When I solve to isolate it, I get negative 3y over 3x plus 2y. So remember, that's our first derivative. We're asked to find the second derivative here. And once again, I'm going to be using the quotient rule. That's very, very common in these problems. I'm going to fill in my original functions and then substitute in my derivatives. The derivative of negative 3y is negative 3 dy dx. The derivative of 3x plus 2y is 3 plus 2 dy dx. And I have a couple of places where I can substitute in here. Remember, we don't want our derivative to have dy dx in it. We want it only in terms of x and y. So I'm going to substitute in here whatever dy dx is into both of those spots. And there we have our second derivative for number 5.